Okay, guys, we're going to be looking at the electric field at a point P along the center axis of a ring of charge. If I look at all of the little tiny DQs that make up the electric field, right, this is a continuous charge distribution, but I need to find the contribution from each one of these charges. What I want you to consider is that for every charge on this ring, there's a symmetric charge about that green axis, a symmetric charge on the other side. Right? So every single one of these charges has a pair on the other side. And what that's going to do when you look at the electric field, right? These electric field lines and the contribution to the electric field from charges that are on opposite side of that axis are going to look similar to this. The contribution from this little charge down here would be sort of up in that direction. A contribution from a charge up here would be kind of down in that direction. And then when I add those two vectors together, it looks like I'm only going to need to consider the electric field in the x direction along this axis, right? All the components of the electric field in what we'll call the y direction is going to cancel out. Okay, so that's going to simplify this a little bit because of the symmetry. The other thing that is nice about the ring of charge, for example, if you look at the geometry of this situation, sure, we are a distance of d away from the ring of charge, from the plane of the ring. The ring itself has a radius of capital R, so for one little tiny dq, it would have a distance of little r, right? And when we go to do the integral to figure out the contribution from each of the charges, it looks pretty complicated. You see this right triangle here, where little r is the hypotenuse and r and d are the legs. But what's really nice is that if you look at the geometry, because the plane of the ring itself is always a distance d away from the point P, our right triangle doesn't change for any of the points on the ring. So it actually tells us that little r is a constant in this situation, and that makes things pretty simple, to be honest. So what I'm going to do real quick, I'm going to try to stop it at the top. Cool. And then I'm going to bring this guy into Smart Notebook so that we can start deriving the electric field at point P. Okay. So let's get rid of this and give me that image there. Right. It's a lot better than I can draw. So I chose to animate it here because my drawings are pretty awful. All right. So we know that to get the total contribution to the electric field at point P, we need to add up the contribution from each of the little tiny point charges. And each of those tiny point charges contributes a little tiny electric field of dE. So we'll be adding up from 0 to the overall electric field at point P. Okay? And then what we said was we're going to add up K dq over little r squared for all these little charges. But then when we look at the electric field and we consider the symmetry that there's always going to be an electric field symmetric about this axis, I only have to consider then this component. So what I'd like to do now is add a little theta in here inside of our right triangle with dr and little r. But that theta would also be the same as this little guy right here, right? So if I'm looking at the contribution to the electric field from this charge right here at the top of the ring, I would only need to consider this guy, which is dEx. Let's call this the x-axis, right? But k dq over r squared, that is dE. That's the magnitude of the electric field because of this one charge. So what I want to do then to get dEx would be dE times the cosine of that theta, right? So when I'm adding up all these little tiny contributions to the electric field, I'm going to do dE, but then times the cosine of theta. So I'm only considering the x component. Okay, great. Really, the integral on the left side is pretty easy. When you do the integral of 1 dE, you just get E. So the electric field at point P is going to be the integral of k dq over r squared times the cosine of theta, right? So now I need to go up and look at that right triangle. And it looks like I've got an expression for little r from Pythagorean theorem. I could say that r squared is d squared plus big R squared, right? And you'll notice here in my integral, I've got an R squared in the denominator. So I can go ahead and replace that with d squared plus R squared. And the only thing I haven't taken care of is that cosine of theta, right? You'll notice that theta doesn't match dq, so I've got a problem, and I need to go ahead and try to substitute something for cosine of theta. But again, I've got this right triangle, and it looks like if I take the cosine of this theta, then I would get adjacent over hypotenuse. So I can say cosine of theta is the same thing as d over little r. Oh, but I don't want a little r, right? Little r is appearing to be a variable. I just showed through Pythagorean theorem that little r is not a variable. Little r squared is d squared plus r squared. So I'd like to take care of that little r to simplify this integral, and that's going to be, well, if r squared is d squared plus r squared, then little r to the first would be square root of d squared plus r squared. I'm going to go ahead and replace that. For cosine of theta, I'm going to put in d over the square root of d squared plus r squared. So that is d over the square root of d squared plus r squared, which I'm going to write as to the 1/2 power. Okay, looks like I have that similar term on the bottom, d squared over r squared to the first, or to the 2/2, times d squared plus r squared to the 1/2, and that's going to give me on the bottom kd dq over d squared plus r squared to the 3/2 power. Okay, great. Let's make sure that all of our rules for integrating have been satisfied. Everything is attached to a small factor. Right now that factor is dq. The second rule, make sure that all of the variables are attached to the correct small factor. Well, k, d, and capital R are all constants, right? Based on the geometry up here, capital R is just the radius of the ring. D is the distance from the center of the ring to the point P. Those aren't going to change no matter where I am on the ring. So this actually becomes a pretty simple integral. This is then just the integral of k d over d squared plus r squared to the 3/2 times the integral of dq. Well, it's probably a good time now to decide what are my integration bounds. How do I make this a definite integral? Well, when you start out, you've added no charges and no contribution of charges to get that electric field. And at the end, once you've added them all up, you should end up with a total charge of capital Q. Great. Well, that's an integral that I'm prepared to do. E at point P is just kd over d squared plus r squared to the 3/2 times, again, the integral of dq is just q, evaluated from 0 to q, gives me a q to the first power. All right. So that's it. That's the electric field at point P along the center axis due to a ring of charge. And a couple of things I want to do here is I want to look just to see if I can recover that expectation of kq over r squared. Let's see if I can get something similar to that. That idea of a point charge if I get really, really far away from the ring. So what would happen if I was really, really far away from the ring? Well, capital D then is much, much bigger than the radius of R. If I'm really far away from this ring, I'm hoping that I lose the geometry and I should get something that looks kind of like a point charge. So let's look at that. Let's look at what happens if D is much, much greater than R. If D is much, much greater than R, then the electric field is going to look something like this. I'm going to make it approximate because I'm about to pull some things out. And that is k dq over, well, if I know that D is much greater than R, then I want to get a ratio of R to D. So I can basically call that guy 0. So let's go ahead and inside of this 3/2 power, let's pull out a d squared. So I get d squared times 1 plus r squared over d squared. And again, all of this was to the 3/2 power on the bottom. Great, you're noticing here I've got that r squared over d squared. That is a very small number because the numerator is much smaller than the denominator. So I can essentially call that guy 0. And then when I distribute this d squared, I just get d squared times 1 to the 3/2 power, right? So the electric field at point P is approximately K d Q over, well, d squared to the 3/2 power is d cubed, but I've got a d on top already, so that becomes a d squared, and this guy is roughly kq over d squared, right? And that's basically what we'd expect for a point charge. Really far away from this ring, we lose the geometry of it. We lose the shape of it. We have no idea what that distribution looked like, because far away it just feels like it was a point charge of total charge q. Okay. The next thing I'd like to do is take a look at this situation. Well, if this is a positive ring of positive charge q, putting a positive charge at point P wouldn't be really exciting. This positive charge would just get kicked off and it would accelerate off in the x direction and it would never come back. But I think it would be a lot more interesting to consider, instead of a positive charge, what happens if you place a negative charge right there, right? And you notice then if the electric field is pointing in the x direction, then the negative charge would want to move in this direction, right? Looks like a restoring force. It looks like it's trying to push or pull this negative charge back towards the ring. But what's going to happen when this negative charge goes beyond the plane of the ring? Well, now the electric force is going to be back towards the ring again. So this electron or this negative charge is going to want to oscillate back and forth along this x-axis. Well, that sounds a lot like simple harmonic motion. So what I'd like to do, I think, just looking at this electric field and noticing, that the force that a charge would feel in that electric field is QE, right? This doesn't look like a linear restoring force, right? This electric field and then this force is going to be proportional to D over, D squared plus R squared to the 3/2, right? And ultimately, that is not equal, or that is not proportional to the displacement to the first power. That's what we want to see for simple harmonic motion. We want to see the displacement to the first power, a linear restoring force. And of course, this is not linear restoring. So while this would be periodic, it would not be simple harmonic motion. It wouldn't be anything as simple as a sine or a cosine. But what I think we can do is, if we look at just a very small amplitude, you only pull this negative charge out to a small amplitude. So we're looking at a really tiny capital D. Okay? If I pull that to a small amplitude, especially compared to the size of the ring, and I look at what happens if R is much, much greater than D. If R is much, much greater than D, then the electric field at point P is going to look like this. Well, again, we have K dq over D squared plus R squared to the 3/2. So I'm going to say K dq over R squared plus D squared to the 3/2. Okay? But if R is much, much greater than D, then I want to get a ratio of D to R. And I'm going to do that by pulling out an R squared. So the electric field at point P is K dq all over R squared times 1 plus D squared over R squared. And that's all to the 3/2 power, of course. But D squared over R squared is essentially 0, because that ratio is going to be really, really tiny. And again, I'm going to have R squared times 1 to the 3/2 power. So that's going to give me an R to the 3rd. So the electric field at point P is approximately, again, approximately now because I've made this assumption right there that that's 0, is K dq all over r to the third power. Well, remember that k, q, and r are set up. K is a constant, q is whatever the charge of the ring is, and r is the radius of the ring. Those guys are not changing. Of course, d will change once you release the charge. When you release the charge, you let the particle go, and it starts moving along the x-axis, d is going to change. So in this particular case, right now, d is a variable. When we did this problem, we were looking at a static situation. What is the electric field just at this point P? Right now, that point P was a distance of d away from the ring. Okay? But recognize that when you let that charge go, when you release it, d is going to decrease. It is a variable. Okay? So let's look at this electric field and then the force on a negative charge. The force on a negative charge. If I place a negative charge at position D, I know that the force is Q times the electric field. Well, the electric field is going to be pointing in the opposite direction that a negative charge is going to move, right? So I'm going to say a couple things here. I'm going to say force is MA is equal to, I'm going to put a minus here to recognize that this is going to be a restoring force. This is going to be a force in the opposite direction of the electric field because it's a negative charge. So I'm going to say then Q times the electric field K D Q all over R cubed. And the reason I decided to put D back here is to show now that this is in the form of simple harmonic motion. What we required for simple harmonic motion was a linear, d to the first power, restoring force. Linear restoring. So the next thing I'm going to do is just divide by m so that I can get my second order differential equation. So this is minus q k q over m r cubed d to the first power. But we know acceleration is just the second derivative of position with respect to time is equal to minus q k q over mr cubed, and again d to the first power. Great. So now, as we did with simple harmonic motion, if I have it in this form, I can find the period actually that minus charge is going to oscillate back and forth through the ring. And we do that because we know that this guy, whatever is in front of x or whatever is in front of the displacement, is omega squared. So I can say then that omega is just the square root of qk times capital Q over mr cubed. And we know the period of this oscillation is going to be 2 pi over omega. And again, I don't like having that fraction and that square root in the denominator. So to bring it up, I'm going to go ahead and flip that fraction over. So this guy is going to become 2 pi times the square root of mr cubed over q times k times q. And that's the period of oscillation for a negative charge with a small amplitude along the center axis of this ring of charge. Cool. So next we're going to do electric potentials. We're going to get into some of the calculus of that, and I look forward to doing those videos for you. All right.